Okay, let's look at three examples here, and we're going to talk about the continuity of these functions, or I guess I should say we're going to talk about the discontinuity of these functions, and they each are going to have a discontinuity. I just want to know what kind of a discontinuity is it? Is it a removable one or is it a non-removable one? And if so, where? Okay, so let's look at this first example, and we'll go to the calculator to first look at a graph of it. And here's the function, and let's bring up the graph. And a little bit difficult to see because of the resolution of the calculator, but you can see that my function looks like it starts here, comes to the left, and then runs down. It runs down the y-axis here, and then it picks up over here, and then runs this way. Okay, one thing you'll notice from the function is that 0 is not a member of the domain. Okay, so clearly we're going to have a discontinuity because the domain of this function is all real numbers except for 0. So 0, when we get to 0, no matter what we're doing with our pencil here, as soon as we get to 0, we have to lift our pencil up and jump over 0 and retrace the final part of the graph. Well, you can see that we have a vertical asymptote here at 0, and there's no way to redefine where 0 goes in order to make this function continuous. Okay, so this would be an example of a non-removable discontinuity. So we could write non-removable at x equals 0. Okay, that's where we had our vertical asymptote at 0. All right, let's go ahead and look at the second function here. And the second function appears to be quadratic at first, but if you look carefully at the graph, let me get back to my y-editor here, and I will change to my second function. Okay, so here's my function here, and you can see the graph that it spit out. Let's blow it up a little bit. Okay, so it looks linear. This looks like a line. Now, in previous videos, we've looked at why this might do that. But this is also a good example of why not to trust your calculator. This function, just based on the graph, looks like it's continuous everywhere. Okay, it even looks like it's continuous right here at 1. If you look at 1 looks like it gets mapped right up here, maybe to 2 or something. Okay, but if you look very carefully back at the original function, you'll notice that 1 is not in the domain of your function. Okay, so really, what we can do is we can rewrite this function. Whoops. We can rewrite this function and notice that the top factors to x plus 1 times x minus 1, and the denominator is just x minus 1. Okay, now one thing you'll notice is that we have an x minus 1 up top and an x minus 1 down below, and we can rewrite this function as x plus 1. Okay, so it looks like this function here and this function here are identical functions with the exception of maybe at one point, and that one point is going to be 1. 1 is not in the domain of this function, but 1 is in the domain of this function. Now, if we consider that and we go back to the calculator, this really does look like the graph of x plus 1. It goes through the y-intercept at 1, looks like it has a slope of 1. But this is a little disconcerting here. We know that 1 is not in the domain of this function right here. So what's going on? Well, it's a calculator thing. That's about as good as I can tell you. The calculator is quite literally plotting some points and then connecting the dots. And it must not have tried to plot 1, otherwise it would have got an error. So it probably plotted a point over here, maybe 0.5, and then plotted a point to the right of 1, maybe 1.5, and then just connected the dots in between them. Okay, so a little trick to ensure that it actually plots 1. is I'm going to go to my zoom menu and do a zoom decimal. If I do a zoom decimal, notice what happened. Okay, we get this little gap now where 1 should be getting mapped to. Okay, so this is still a line, but now it reveals the whole, and clearly this looks like a removable discontinuity. It looks like we started with the line and we just kind of plucked out this little area right here. All right. The other way I think of it, of why it's a removable discontinuity, is we have removed one of the factors. Okay, if we have a function and we can rewrite it in terms of another function so that it agrees with the first function in all but one point, what we've done in essence is we've removed one of the factors, and this is how I remember that we're dealing with something that has a removable discontinuity. Okay, so this function has a removable discontinuity at 1. Okay? And finally, the last example. The last example is a piecewise function. And you can probably guess where our discontinuity is going to occur at. Here we have a linear function. We know linear functions are continuous everywhere. Here we have a quadratic function, and this is going to be continuous everywhere. So really, we have two continuous functions here. Okay, if I put them together, am I going to have a continuous function, or am I going to have maybe perhaps a discontinuity somewhere? We don't know until we examine the graph of it. Okay, and if we look at the graph, let me turn off the last function. Here we go. And I'm just going to do a zoom. I'm going to get back to a standard viewing rectangle. I'm going to do a zoom 6. And here we go. Okay, this piecewise function appears to be continuous, but don't be fooled by your calculator. There could be a little hole in this function right here. And remember that things are changing right around 0, so 0 is probably where my discontinuity is going to happen. So if we go back to the original function, actually what we could do, just to do a little bit more analysis on the graph, I can actually turn my axes off, because sometimes you'll get a hole that exists right on the axes, but because your axes are drawn, it doesn't look like there's a hole. Okay, so I've turned my axes off, and it doesn't look like there's a hole right here. Okay, so the next thing I'm going to do is I'm going to do a zoom decimal to make sure that 0 really does get plotted. Okay, remember that 0 is right about here. And it looks like there's it doesn't look like there's a discontinuity here at all. It looks like it's just a nice, smooth, continuous curve. In other words, here's my line. Here's the line x plus 1. And where x plus 1 stops, x squared minus 1, or whatever it was, what was it? X squared, I forgot what it was now. Let's get back here. X squared plus 1. Sorry about that. Okay, x squared plus 1 is going to take off. This is our parabola right here. So from the graph, just looking at the graph, it doesn't look like there's a discontinuity here. So I'm kind of leaning towards this thing is continuous everywhere. Okay, one way to make sure is we know this is continuous everywhere. If I map where 1 gets sent, where is f of 1? Okay, well, f of 1, we know that if we're less than 0, less than or equal to 0, we're going to get mapped to this line. But if we're greater than 0, we're going to get mapped to this parabola. So what does f of 1 actually equal? Well, it's going to equal the input squared, and then I'm going to add 1 to it. Okay, so evaluating that, we get 2. So f of 1 equals 2. Now, in determining if this other function picks up where this guy leaves off, I'm going to just substitute 1 into this other function. Now, we know that 1 actually gets mapped to this parabola right here, but to see if this line picks up where this guy leaves off, I'm going to actually just substitute 1 into my linear function, and I see that it also equals 2. Okay, and that's a good indication that these two guys are going to meet at 2. If this number were different, you would probably see one of these jump discontinuities, like we saw in some of the prior examples a couple videos ago. Okay, so this would be an example of where perhaps your value that you're interested in gets mapped to one value using one function, but then we have this great big jump as soon as we get to our other function. Not so in this example. Okay, this example, we saw that we had the line x plus 1. Okay, and when we were at 0, we got mapped to this line, and anything below 0 we got mapped to that line. But then at 0 we have this switch to this function where it just kind of picks up where that line leads off, and this is our parabola from there. Okay. All right, so those are some examples that help illustrate what a non-removable and a removable discontinuity is. In the next video, we're going to look more at continuity and describing a function in terms of its continuity as opposed to its discontinuities. See you there.